Hello everyone. In this video, we're going to look at an application of exponents known as scientific notation. So most of the numbers that we deal with on a daily basis are considered to be quite tame, falling somewhere between maybe -1000 and +1000. Think of daily temperatures, for example. They're usually less than 100 degrees Fahrenheit. Cars usually cost less than 100,000. Average human height is less than 6 feet. Grocery totals are usually less than $100. Average daily speeds are less than 60 miles per hour. And that's not the way all numbers are, of course. Scientists usually deal with numbers that are either mind-bogglingly small or mind-bogglingly large. Just a few examples. The most probable distance between the electron and the nucleus of a hydrogen atom is, for example, approximately 5.29 times 10 to the -11 meters. Now, this right here is the very compact scientific notation version of the number. If you were to actually write this out in the standard notation we're used to, it would look like this. So it would be a decimal point for 10 zeros after it, and then 529. So it would be take a lot more effort to write that down compared to this. 1 mole of water, which is around 18 milliliters of water, or if you want to be real practical, a few drops of water, basically. It contains approximately 6.02 times 10 to the 23 molecules of water. This huge number, of course, is given in scientific notation. If you look at the standard notation, it translates into this: 602, and then look, 1, 2, 3, 4, 5, 6, 7. That means 21 zeros after 602. So you can see the kind of numbers scientists deal with, right? And that's just in a few drops of water. That's how many molecules of water are in just a few drops. In fact, 1 mole of anything contains that many items of that number. It's called the Avogadro number. The distance between the Sun and Icarus, which is the farthest star ever observed, is 9 billion light years. Now, 1 light year is the distance that light travels in 1 year. A lot of people, when they hear the word light year, because of the year, they think it's a measure of time. It's not. A light year is actually a measure of distance, and it's how far light travels in 1 year. Well, you may say, well, traveling in 1 year, how much could that be? Well, the point is that there's nothing in this universe that travels faster than light. Light is the fastest entity that we know. And if you count this in miles, this large distance is approximately 5.29 times 10 to the 22 miles. So if we were to convert the light years into miles. Now, if you write that in standard notation, it would look like this. So think of it as 52,900 billion miles, okay? So when you see the difference in scientific notation and the standard notation, you can see why scientists are very interested in scientific notation. In fact, if they were stuck with nothing but standard notation, they would be spending most of their days just writing numbers. They would hardly get any time to come up with any significant discoveries. However, this doesn't mean we should dismiss standard notation, because remember, it was only when you saw those numbers that we were talking about, the distance between the Sun and the Icarus, or the number of molecules of water in just a few drops, etc., you didn't really feel the amazing size of those numbers, whether they're extremely small or they're extremely large. until you looked at it in standard notation. So scientific notation is extremely efficient, but kind of lacks the heart of standard notation. Standard notation is not necessarily efficient, but it packs a big punch when it comes to giving you a really good feeling about a number and a good understanding of the size of the number. If you noticed at the numbers that we saw in scientific notation, they all had a power of 10 involved in them. So in order to better understand how to convert into scientific notation, we should remember what multiplying by powers of 10 does. If you remember, multiplying a decimal number by a positive power of 10 moves the decimal point of that number to the right. By how many places? Well, by exactly as many places as the exponent of the power of 10. So, for example, when you look at 3.4 times 10 to the 4 and you want to convert this to standard notation, you have to realize that multiplying 3.4 by 10 to the 4 takes the decimal point of 3.4 and moves it 4 places to the right. So if you start here and go 1, 2, 3, 4. Notice we ran out of digits after 1, so what do? You add zeros. That's how you convert. Multiplying a decimal number by a negative power of 10 moves the decimal point of that number to the left by a number of units equal to the exponent of the power of 10. So for example, if you take the same 3.4 but multiply it by 10 to the negative 4, this time it's going to take the decimal point of 3.4, which is right here. Initially, it's going to move it 1, 2, 3, 4 places to the left. That's what multiplying by a negative power of 10 will accomplish. And multiplying a decimal number by 10 to the 0, of course, doesn't move the decimal point at all. Because think about it. What is 10 to the 0? It's 1. So what happens when you multiply a number by 1? Remember, this is 1. Nothing happens, right? You get the number you started with. Okay. So let's take a look at some multiplications by powers of 10. So what essentially this is going to do is, since these numbers are actually in scientific notation, it's going to be a conversion to standard notation. We'll understand scientific notation more accurately in a minute, but all this background will help you understand it better. So for example, with 3.95 times 10 to the 0, remember, multiplying by 10 to the 0 is like multiplying by 1. So this is not going to move the decimal at all. You just get 3.95. Now, when you multiply 3.95 times 10 to the 1, that's going to take the 3.95 and it's going to move its decimal 1 place to the right. So you end up with 39.5. So let's put an arrow instead. All right, so with this one, you start with 3.95 and you're multiplying by 10 squared, so you're going to move the decimal 2 places to the right. So 1, 2, so you end up with 395. All right, so if you multiply 3.95 by 10 to the 5, right? So you're just going to put 3.95. You're going to move the decimal 1, 2, 3, 4, 5. Now, when you round out of digits, you replace them with zeros. So the final outcome is 395,000, right? So 395,000. When you multiply 3.95 by 10 to the 10, of course, you're going to do the same thing. It's just going to take you a little bit longer. You're going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there you go. Replace those with zeros like so. So you have 3, 6, 8. So the final result 395 with 8 zeros. 2, 4, 6, 7, 8. All right, we knew that, of course, because the decimal is going to move 10 places to the right, and once you already know how much 2 to the right is, it's right there. So after that, you're going to need 8 more. So there you go. All right, so basically 39,500,000,000. Okay, so multiplying by powers of 10 that have negative exponents moves to the opposite direction. So you start with 3.95, move the decimal point 1 to the left, you end up with what? 0.395. Multiply 3.95 by 10 to the negative 2. That has the effect of taking the decimal point, moving it 1, 2 places to the left. So we ran out of digits, just like in the other direction. We add zeros, but on this side. So the final outcome, 0.0395. Now, whether you put a 0 on the left of this or not is optional. Most individuals like to put it there, but you know, even if you don't, it's okay. All right, so 3.95 times 10 to the negative 4. So we start with 3.95. You should be pausing and doing this stuff on your own, of course, and then just checking your answer. So you go 1, 2, 3, 4. Decimal is going to end up there, and there you go. So 0.000395 times 10 to the negative 7. Okay, so let's do it without this business now. That was good just to get you rolling. So now you have 3.95. So we're going to move to the left 7 places. As soon as we go 1, we ran out of digits. So how many zeros do you think I need to add here? If you said 6, you were right. So we can just erase this and just put 1, 2, 3, 4, 5, 6 zeros. And then the decimal point. Okay? Of course, times 10 to the negative 10, you're going to end up with how many zeros to the left of the 3? Did I hear you say 9? You're right. 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 3, 9, 5. Like that, okay? So very, very straightforward. All right, so scientific notation has a very specific format. So what is that very specific format? We only consider a number to be in scientific notation if it has this form, okay? So it's written as some real number times some power of 10. But there are some restrictions on what that real number has to be and some restrictions on what that exponent n has to be. The real number a has to have an absolute value. That means it can be positive or negative, that doesn't matter. But its absolute value has to be somewhere between 1 and 10. And the way we say this is we say left inclusive. That means 1 is okay, 10 is not. So you want the absolute value to be greater than or equal to 1, but simultaneously less than 10. So in other words, 9.99 is okay, right? 10 is not. On this other extreme here, 1.0001 satisfies the value for A. 0.99 would not, because it's not greater than or equal to 1. Okay, so any number between 1 and 10, including 1, excluding 10, can be here. And the exponent has to be any integer, okay? Remember what integers are. Integers are the set containing these values. Basically, all the simple numbers on the number line, whether they are negative, 0, or positive. So think of it as all the nice simple numbers on the number line. They form the set of integers, and z is the letter that we use to indicate the set of integers. We use the double bar so that you know this is not just any z. Don't mistake it for just some variable. No, this is the set of integers when you use that notation. So here we have some numbers in scientific notation. So notice this number here is between 1 and 10, and that is in fact an integer. Now this number here is negative, so itself is not between 1 and 10, but remember, all we need is the absolute value of the number to be between 1 and 10, and this qualifies because the absolute value of negative 6.01 is 6.01, which is between 1 and 10, including 1, excluding 10. Negative 30, of course, is an integer, so it's fine. How about this? Is that in scientific notation? Of course. 7 is between 1 and 10, and 0 is an integer. Now notice with scientific notation, an old friend of ours makes a comeback, right? We haven't used the cross to signify multiplication for a long time, right? So ever since we started working with equations, etc., we've let this symbol, we've kind of reserved it for x, correct? But this is the one exception. With scientific notation, we use the cross to indicate multiplication. So again here, 1, remember, is okay. You shouldn't have 10 in this location, but 1 is all right, because we said the absolute value of a has to be between 1 and 10, including 1, excluding 10. This is fine because 1.4 is between 1 and 10, and 2 is an integer. Now these numbers are not in scientific notation, and we'll talk about why not. Well, here we can of course see the failure is 52.3. The absolute value of 52.3 is not between 1 and 10. So instead of putting is between, we put a little bar like that. So this the way you would read this is you would say the absolute value of 52.3 is not between 1 and 10. What about this number? Take a look at it. What do you think is wrong with that? Why is that not in scientific notation? After all, this part is okay, right? The absolute value of negative 6.01 is 6.01, which is between 1 and 10. And 10, of course, is all right. There's the problem right there. Remember, that number there has to be an integer. And integers are the simple, nice numbers. No decimals, nothing like that. No decimal point. And no digits after the decimal point other than 0, of course. Here, the problem is that negative 30.5 does not belong to the set of integers. Remember, this notation, when you see it, that's neither E nor C. It's the Greek letter epsilon. In mathematics, we use it to indicate belonging. So when you put, if I put 5 and then this notation and then Z, this means 5 belongs to the set of integers. So when I put negative 30.5, the epsilon notation with a bar through it, that means it does not belong to the set of integers. And of course it should, if this is supposed to be in scientific notation. So that's why it's not. Now this number here, 7, it's not in scientific notation, but it's not far from scientific notation either, because 7, of course, is a number between 1 and 10. So the only reason we say it's not, because we haven't written it in the form of some number times some power of 10. So if I were to actually take 7 and write it in this alternative format, remember 7 and 7 times 10 to the 0 are identical as far as value is concerned. So if I did that, then 7 in this format is in scientific notation. How about 10 to the 10? Well, again, that's a number that is quickly convertible to scientific notation because all I need is to write it in this alternate format and put the 1 there. Because remember, you want to be in the format of a times 10 to the n. So these two, yes, they're not as not in scientific notation as these two. So these are very easily possible to convert to scientific notation. How about this one? This one, of course, is not in scientific notation, not because of the 1.4. That's fine. That's a number between 1 and 10. It's because of the square root of 2. Of course, as you know, square root of 2 is not a member. So another way of saying does not belong to is to say is not a member. Is not a member of the set of integers. All right. So now we know what scientific notation looks like. So we want to start with some conversions. Let's start by converting from standard notation to scientific notation. All right, so here I've tried to make this process as simple as possible for you. So let's start with a simple number like 302 and go ahead and convert it to scientific notation. So the way we're going to do this is the following. We're going to go ahead and start scanning the number, no matter what the number is, as long as it's written in standard notation, right? We're going to scan it from left to right, and we're going to stop after the first non-zero digit. So in this case, you can see that the first non-zero digit is the 3. So we put it there, and we'll go ahead and label it A because this is going to be the location of the decimal point after we move it in order to put it in scientific notation. So we're using A for after. Now, we'll also place a marker at the original location of the decimal point. Remember, when you look at 302, you're saying there is no decimal point. Well, it's a whole number. There's always a decimal point. It's just that if it's a whole number, it comes after the rightmost digit, right? So it's right there. So we put a marker there. This is the original location of the decimal point before we move it in order to put it in the right format for scientific notation. Now we're going to count the number of digits you have to move to get from A, which is the location after the move, to B, which is the location of the original decimal point before it was moved. So from A to B, right? Now, if we end up having to move to the right to get from A to B, the number of digits that we have to move, we're going to give it a name. We're going to call it N. And if we move to the right, we're going to count it as a positive 2. If we had to move to the left, we would have used a negative number for N. So once you calculate that value N, you're almost ready to write your number in scientific notation, because now what you're going to do is you're going to write the new number, which is between 1 and 10, which is basically the same number that you started with, but with the decimal point having moved to this location, 3.02, and then you're going to write times 10 to the power of that number that you calculated here. How many digits did you have to move to get from A to B? 2 to the right, so that's indicated by a positive 2. So 302 is the same as 3.02 times 10 to the 2. Let's quickly go over the procedure again. Scan the number from left to right. Stop after the first non-zero digit. Go ahead and mark that location A for the location of the decimal after it gets moved. Then go ahead and put a marker at the original location of the decimal before any moving. Then calculate the number of digits you have to move to go from A to B. This is very important that you count from A to B, not the other way around. So if that number of digits is a positive, if it's movement to the right, use a positive number. If it's movement to the left, use a negative number. So now you have the A, which is basically the number that you get by the first movement of the decimal to the new location, and then you're going to multiply it by 10 to the power of the n, which you found in order to get from A to B. And now you have just converted your number to scientific notation. We'll do a few examples and this will become easier. All right, so here we're going to convert 0.0302 to scientific notation. So we're going to write down 0.0302. Remember, we're going to scan from left to right, and we're going to stop after the first non-zero digit. Notice that's 3 right there. We're going to mark that location with A. Now we're also going to mark the original location of the decimal point, which is right here. So we're going to call that B. Now, this new number we get by putting the decimal point there is going to be 3.02. So that's what we call A. And remember, the number of digits we have to move, always calculate from A to B. To get from A to B, we have to go 2 units to the left. That means we're going to use a value of -2 for n. Now we just have to write A times 10 to the n, and that's going to be our number in scientific notation. So 0.0302 is going to be 3.02 times 10 to the -2, like that. That's as simple as it gets. So always the same procedure. Scan from left to right. Stop after the first non-zero digit, and that's going to create your new number. So that's going to be your A, 3.02. Now, place a marker at the original location of the decimal point, which was right here. So we'll call that B. B for what? Before any movement. Now count the number of digits you have to go to get from A to B. Notice that's going to be 1, 2 to the left. So we'll use a value of -2 for n, and we write our number. So we get 3.02 times 10 to the -2. All right. All right, so now we want to convert 534 million to scientific notation. I think you should have this down by now, so definitely pause the video and try it on your own before you come back. All right, welcome back. So remember, we always start in the same way. We scan from left to right, and of course if the number is already in scientific notation we'll say so, but notice none of these numbers have been in scientific notation. So we'll move from left to right, we'll stop after the first non-zero digit, which is the 5 itself. So our A, after putting a marker there for capital A, we're just going to call it 5.34. Now remember, ending zeros after a decimal don't count. So I don't need to write all those zeros once I've said 5.34. Putting any number of zeros here is not going to change it. It's still going to be 5.34. So we don't need to put any more zeros. All right, for to get the value of n, we're first going to put a marker where the original decimal point is for this number. Remember, this is also a whole number, so it's right there. So we'll call that b, as in location of the decimal point before any movement. So now we need to count the number of digits we have to move to get from A to B. Notice that's going to be 1, 2, 3, 4, 5, 6, 7, 8, right? So that's going to be the value of n, and because it's a movement to the right, it's going to be positive. So now we're ready to write our number. So our number in scientific notation is going to be 5.34 times 10 to the 8. See how simple that is? If you know the game and its rules, you can play it, but that's what it's going to take. You have to learn the procedure, then it becomes really easy. Now make sure you can understand why that's happening, right? Because that's how multiplying by powers of 10 works, right? So it has to do with this nature of powers of 10, which is very useful. All right. Remember our friend Avogadro's number? So we're going to take Avogadro's number and we're going to write it in scientific notation. I hope you're thinking, wait, what are you talking about? It is in scientific notation. Well, you would be exactly right. That was the whole point of this problem. Because remember, it said if the number is already in scientific notation, just say so. Well, this is already in scientific notation. All right. Every once in a while, we'll throw a curveball to see if you're still up, paying attention. All right. So there we go. We didn't have to do much there. How about this one? Is this number 98.2 times 10 to the negative 6? Is that in scientific notation? Well, it certainly looks scientific notation-ish, doesn't it? It's like kind of looks like it's in scientific notation, but we have a problem, right? The problem is the 98.2. This is not a problem. That's an integer. This is a problem because that's not a number between 1 and 10. So how do we take a number like this and put it in scientific notation? Remember, it's not enough just to have some number times a power of 10 to say it's in scientific notation. This number has to satisfy certain requirements, namely its absolute value has to be between 1 and 10, including 1 excluding 10, and this number has to be a power of 10, and the integer, the exponent needs to be an integer. So we notice here that the only problem is this part, so we're not going to mess with what's already fine. So we leave this alone for now. We're going to carry it. So, but this part, we can take that and put it in scientific notation easily, right? So let's just zoom in on that. Let's look at 98.2. Remember, we're going to scan it from left to right, stop after the first non-zero digit, which is where, right there. We're going to call that A. Where is the location of the new, the original location of the decimal point? It's right there. So we call that B for before moving. So the new number is going to be 9.82 after the move of the decimal point. And how many? So A is 9.82. And what is N? N is the number of digits you have to move to get from A to B. So how many places? To get from here to here, that's just one place, right? So N equals 1. So we're going to write 98.2 only. Leave this part alone. Imagine that's not even there for a minute, okay? You're just looking at 98.2 and you're going to put it in scientific notation. So it becomes 9.82 times 10 to the power of 1, right? Think about it. What is 9.82 times 10 to the power of 1? That just moves the decimal 1 to the right, so it's 98.2. So we just did the correct conversion. Don't forget, we still have times 10 to the negative 6, right? So now all you got to do is, you see that multiplication? You should know how to handle that, because you're multiplying two powers with the same what? With the same base. What's the rule? X to the m times x to the n. What is it? X to the m plus n. Product rule for exponents. So you get 9.82 times 10 to the negative 5. There you have it. You have just converted 98.2 times 10 to the negative 6 to scientific notation. It becomes 9.82 times 10 to the negative 5. All right, so don't be misled by the appearance of things. That kind of looks like it's in scientific notation, but it doesn't satisfy both the requirements, where this number needs to be between 1 and 10, including 1 excluding 10, and this number needs to be an integer. How about the number 1? Is that in scientific notation? Not quite, right? But it's not far either, is it? Remember, you can take 1 and you can write it as 1 times 10 to what power? What power of 10 is it that if you multiply by any number, it doesn't change it? That's what we need, right? Because we want 1 to remain 1 as far as the value is concerned, right? And I think you know, right? That would be 10 to the 0. So we just took 1 and we wrote it in scientific notation. Simple as that. Of course, that should give you a clue. You can do that with any number between 1 and up to 10, right? So if I give you, say, 9.99 and I say put that in scientific notation, well, you don't have a whole lot to do you? Because 9.99 itself is fine. So you don't want to mess with that. You want to leave it as is, and you're just going to bring in 10 to the 0. Or what if I gave you negative 3.72? Same business. Remember, negative 3.72 has an absolute value, which is 3.72, so it's already fine as far as the value of a is concerned. So you just need to multiply it by 10 to the 0, and you should be good to go. Okay? That's that. Now let's go ahead and convert from scientific notation to standard notation. We've already talked about this in the beginning of the lecture. This should be quite easy at this point. So all that's going to require is understanding what multiplying by a power of 10 means, which we talked about earlier. So if you have 3.4 times 10 to the 10, then just start with 3.4 and move the decimal 10 to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you run out of digits, put zeros. All right, so you're finished basically. Just now move this decimal and put it there. Okay, if you want to write it more nicely, of course that's going to be 9 zeros after 34, right? So 34, 1, 2, 3, 1, 2, 3, 1, 2, 3. If you want to write it properly, you can start on the right, count every 3 digits, put a comma. Now you can see it, right? It's 34 billion. All right, so we're going to write this number in standard notation. So we're going, remember, the sign isn't going to change. So we're going to start with negative 5.314, and we're going to move the decimal 6 places to the left. We ran out of digits as soon as we move 1 place, right? So we're going to just go 2, 3, 4, 5, 6, like that. And we're going to move the decimal that many places, and we're going to put zeros after we run out of digits. So now we have our number, negative point, notice 5 zeros, and then 5, 3, 1, 4. Okay? So that's that. You just took this number, which was in scientific notation, and you wrote it in standard notation. So all you need to know is what multiplying by powers of 10 does to a number, which we talked about earlier in the section. Don't forget the sign is not going to change. All right, we're getting close to the end of this section, and now we're just going to look at a couple of operations in scientific notation. So let's say you want to multiply these two numbers, okay? They're both obviously in scientific notation, and in order to write the outcome you don't need to convert them to standard notation or anything like that. We're just going to work with scientific notation. So what we need to do is first multiply 1.5 by 7.2. Let me go ahead and get a calculator so we can do that. All right, so we're going to multiply 1.5 by 7.2. So we get 10.8 times. Now, those two powers of 10, we can go ahead and multiply, remember, using the product rule. X to the m times x to the n equals x to the m plus n. Here, the x is being played by 10. So we keep the 10, the base. We add the exponents. 11 plus negative 15, that's going to be negative 4, right? Remember, when you have 11 plus negative 15, that's just 11. Positive times negative is negative. That's just 11 minus 15, which is negative 4. So now we're going to have to go one more step, right? Because remember, this is not in scientific notation yet. Usually when they give you a problem like this, they expect the answer to be in scientific notation as well. So it's close, but not there yet. We already saw what we need to do. We just need to deal with this part first. So 10.8, we're going to zoom in on that. How do I turn that into scientific notation? Remember, scan from left to right, stop after the first non-zero digit. So that's going to create your new number, 1.08. So we put a marker here, call it A, put a marker there, call it B. So we get A equals 1.08. That's the new number with the new decimal location. And N is the number of places you have to move to get from A to B. Notice one place to the right, 1. So basically 10.8 is the same as 1.08 times 10 to the 1, right? So we're going to replace 10.8 with 1.08 times 10 to the 1. Don't forget, we already had a 10 to the negative 4, which needs to carry. So now we get 1.08 times 10 to the negative 3. And now we have the result in scientific notation. Okay? So if the first operation ends up giving you something that is not in scientific notation quite, make sure you put it in scientific notation before you stop. All right, and here's the last one for the road. So notice here, we're dividing two numbers that are in scientific notation. So here we're going to go ahead and take care of that division. That leaves us 1 and 2. So let's go ahead and divide it. What's 1 divided by 2? That's 0.5. So we get 0.5 times 10 to the Now we're going to use the quotient rule. Remember, the cross-canceling business that I showed you when we dealt with only positive exponents, you never utilize when you're dealing with negative exponents. Just use the quotient rule. It's easier, less problematic. So you get x to the m minus n, right? So we get -9 minus -20. Now remember, those two are going to turn into a plus. So we get 0.5 times 10 to the -9 plus 20 will give us 11. Now remember, the 0.5 needs work, right? We need to put that in scientific notation. We're going to move from left to right, stop after the first non-zero digit, which is 5 itself. Put a marker there for A. Then put a marker at the original location of the decimal. So the new number is 5.0, which we don't need to write. Just put 5 times 10 to the power of what? Well, let's see. To get from A to B, you have to move one digit to the left. So the value of n is going to be -1. So we just wrote 0.5 in scientific notation. Okay? So we can say 5 times 10 to the -1, and all that indicates, all of that is just 0.5. So we still have to bring in the times 10 to the 11, right? So now leave the 5 alone and go ahead and multiply those two powers of 10. Of course, using the product rule. So we keep the base and we add the exponents. -1 plus 11 is 10. So there is our result in scientific notation. Now, it doesn't always turn out that you have to do an extra step. Like, for example, if instead of what you have, if we had 8 times 10 to the -9 over 4 times 10 to the -20. Remember, this is a new problem, right? Then notice here 4 and 8 would have left you 2 on the top. So you would get 2 times 10 to the power of -9 minus -20. Those again become plus. So you end up with 2 times 10 to the 11. So in this case, notice that's it. The number, the outcome is in scientific notation, so we stopped, right? Only if the outcome doesn't end up being in scientific notation do we have to do an extra step to get it into scientific notation. Okay? All right, so there is our little gift from the mathematical community to the scientific community. So that's it. You'll be using this in many different scenarios in classes. You'll be reading papers, you know, sometimes, and you'll see articles using scientific notation. So it's a wonderful skill to have. All right, so that's it. Make sure you practice and stay safe till our next video.